In this video, we're going to be going through the medium difficulty questions on equations of motion. As usual, use this to either mark your work or to help you with some of the more difficult questions. Question 1a. A car initially at rest begins to move with an acceleration of 1.5 meters per second squared. Calculate the speed after 20 seconds. So we need to write what we know from the question, because it's going to be a SUVAT one because it's a constant acceleration. So our initial velocity is u. Our final velocity is our unknown. Our acceleration is known from the question, 1.5, and the other thing that we know is the time. So we need to look at those values and work out which equation we're going to use, and it's going to be v equals u plus at. So v is going to equal 0 plus 1.5 times 20, so v is equal to 30 meters per second. Part B, calculate the distance travelled. So this time we've got all of the same knowns, but this time we're working out our distance travelled. So we're going to use the equation x equals ut plus half at squared. And this time t is equal to 10 seconds. So we're going to pop in all of our numbers. So x equals ut, u is 0, so the first bit is just going to turn to 0, and we're going to be typing into our calculator half times the acceleration, which is the same one as above, times 1.5 times the time squared. And if you type that into your calculator, you get 75 meters. 1c, calculate the distance travelled. So this time we're working out x again, but it's going to be t is equal to 20. So it's exactly the same as the question above. X equals ut plus half at squared, but instead this time we have t equals 20. So again, x equals ut, which is going to be 0 plus half times the acceleration of 1.5 times 20 squared, and that's going to give you x equals 300 meters. Question 1d. So figure 1 shows the graph of acceleration against time. So let me just put that in red so you can actually see that line. So it's constant acceleration at 1.5 meters per second. We need to plot the speed and the distance time graph. So we're going to use our answers from the previous page. So the speed got up to 30 meters per second in 20 seconds. So I'm just going to label this one as 30. Doesn't really matter which one you label for this one. And then we're just going to draw a straight line going to 30 at 20 seconds because it was a constant acceleration, which gives us a straight line. For our distance, we've got two bits of data that we worked out. So at 10 seconds, it had gone 75 meters. So we'll make sure that's in meters. And then if we carry on with that axis up here, this one's going to end up being 300 meters. And at 20 seconds, it was 300. So you're just going to draw a smooth curve that goes through 75 meters at 10 seconds and 300 meters at 20 seconds. Question 2a. A digital camera was used to obtain a sequence of images of a ball being struck by a tennis racket, and the camera was set to take an image every 6 milliseconds. The successive positions of the racket are shown in figure 1. So the ball has a horizontal velocity of 0 at A and reaches constant velocity at D, and it travels 96 centimeters between D and G. Calculate the acceleration of the ball between A and D. So we're going to need to know its initial velocity, which we already know, it's just 0, and its final velocity. So we need to work out its final velocity at D, and we can do that using speed equals distance over time. So the distance that it's gone is 96 centimetres, so I'm just going to put that into meters to make it easier. 0.96 meters, so just under a meter. And the time that it's taken, so to do that, we're going to work that out from this 6 milliseconds. So it's taken, if we count 1, 2, 3, it's going to be 3 times 6 milliseconds times 10 to the negative 3. So there's just 4 images if you include the D. But we don't need to include that. How much time has passed is only going to be 3 times 6 milliseconds. And if we type that into our calculator, we get the speed is 53.3 meters per second. It's in meters per second because we've converted both our distance into meters and our time into seconds. We know that its initial velocity is 0. So to work out our acceleration, it's going to be the change in velocity divided by the change in time. So our change in velocity is just going to be our 53.3. Technically, we would need to take away our initial velocity, which is 0, and then we're going to divide it by the total time, which, similar to our last question, the time is going to be between A and D. We've got 4 different images, but that's only 1, 2, 3 different sort of time gaps. It's going to be 3 times 6 times 10 to the negative 3, exactly the same time as we used for the first one. And you're going to get 2963 meters per second squared because it's acceleration. And if we're going to put this to a sensible number of significant figures, we could do that to 2 significant figures, which would be 3,000 meters per second squared. On to 2b. At D, it was projected horizontally from a height of 3.4 meters above the ground. Show that it would fall in about 0.8 seconds. So we've got our initial velocity. So if it's going to be projected horizontally, we are now thinking about it going down. We're thinking about its vertical components. So its initial velocity is actually going to be 0 because it is being projected horizontally. We know its acceleration is going to be 9.81 meters per second squared because it's going to be due to gravity. We know the displacement above the ground is 3.4 meters. And finally, we are working out its time. So we're going to say t equals t, and we're going to work that out and hope that it gives us 0.8 seconds as an answer. The equation we're going to use here is x equals ut plus half at squared. So x is equal to 3.4. Ut, our u is 0, so that's, we don't need to put anything in there. Do half times 9.81 times t squared. We're going to rearrange this. So to find out t, we're going to do the square root 3.4 times 2 divided by 9.81. And we end up with t equals 0.83, which is roughly 0.8, which is what the question wanted us to prove. Question 2c, calculate the horizontal distance the ball will travel as it leaves the racket before hitting the ground and presume only gravity acts on the ball as it falls. So we're talking about its horizontal distance this time. And what that means is its acceleration is going to be 0. It's not going to be accelerating at all due to gravity because we're just talking about its horizontal components of velocity. So its velocity is going to be constant. So we can just use speed equals distance divided by time. So we want its distance. So we're going to do speed times time. We can use our time that we worked out in the last question, or we could just use what they gave us, which was 0.8. You can also use your 0.83. And we're going to times it by the speed, which we worked out earlier as well, 53.3 times 0.8, and we get 42.7. If you do use your answer of 0.8325 from last time, you'll actually get an answer of 44 meters. Both of those would be correct and marked correct. And finally, for question 2, explain why it does not actually travel this far before it's going to hit the ground. And that's because its air resistance is going to cause some horizontal deceleration. So usually for these kinds of questions, we presume that the horizontal velocity is constant. There's no acceleration, there's no deceleration. In reality, there is air, which causes air resistance, and it's going to mean that it decelerates slightly horizontally, so it won't get quite that far. Question 3. Figure 1 shows the variation of velocity with time for a Formula 1 car during a test drive along a straight horizontal track. State and explain which section of the graph shows the acceleration was uniform. So I'm going to zoom in a little so you can see the graph nice and big. We are looking for the straight line, a straight incline. So I'll get my ruler out. and I think it's around 3 that the straight line starts to curve, around there. So which section of the graph shows the acceleration is uniform? It is going to be between 0 and 3 seconds. So that's our first mark for stating it. It is a 2-mark question, so we've got to state why it's uniform as well. And that is because the gradient is constant. And the gradient, and this represents the acceleration. Because acceleration is the change in velocity over time. And if we just look at this graph and work out the gradient there, it would be the change in velocity divided by the time, the change in y divided by the change in x. Going on to question B, determine the distance travelled by the car in the first 5 seconds. So I've added some annotations to the graph question so you can see how you could estimate the distance travelled by the car in those 5 seconds. So it's basically the area under the graph. It's a curve, so we're not expected to do this mathematically, but we can estimate it. So what I've done is I've drawn lines at all like the big square. So that means every 5 seconds I've drawn a line, and every 20 meters per second I've drawn a line. And what we can do is we can count the number of big squares that there are. So there is roughly 19, if you were to count them, full squares. And then there are all these little sections of half squares as well that we can add up, and we can estimate how many big squares there are in total. So I have done that, and I have estimated there are about 21 large squares. You might have counted a few more, 21, 22, 23. So what the value of a large square is 20 meters per second times 1 second. So each square is worth 20. And then what we do is we do our 21 times our 20, and you get 420 meters. So any answer for this question was acceptable in the range 420 to 460. I have not seen this style of question on a WJEC exam question paper. It does seem to come up though in AQA. Part C says show the instantaneous acceleration is about 16 meters per second when t equals 5. So I've gone ahead and marked up the graph again, how you'll need to. So first thing I did is I did a cross at t equals 5 and where it hits our graph. So that is this cross here. And then I drew a tangent to the graph. So you get your ruler and you try and line it up with the curve of the graph, and then you draw a straight line right across your graph. And then we need to work out the gradient. So that's the change in y divided by the change in x. So if we have a read this one, I've drawn all the way from 200 and it crosses our axes at around 80. And then underneath we've got our time, which is 7.6 on this tangent, maybe slightly lower, 7.5, it's around that. And then we type that into our calculator and I got 15.8 meters per second minus 2. And it's said to show it was around 16. So that you're going to get slightly different numbers depending on what your tangent looks like, but there is room for error in the mark scheme. This one says any range is at any value in the range 15.5 to 16.5 is acceptable. You can't use a Suvat equation for this because it hasn't got a constant acceleration throughout our curve, it is changing. Question 3D, so this is a quality of written communication 6-mark question. It's on the forces, which we haven't fully covered in this module yet. So I've just taken a photo of the mark scheme for you and put that in there so you can have a look at where you get the marks if you've given this a go. So what you need to do for this question is explain why the velocity is changing on our car. So I'll talk through the answers. So our velocity is going to increase, or our car accelerates, because our driving force, the force forward, is larger than the resistive forces, which are our forces that would keep it stationary. At the beginning, we've got our maximum acceleration because we have no resistive force, and this is going to increase as our velocity increases. So our drag is also going to increase. It's proportional for the velocity squared. The resultant force is going to decrease as we increase our velocity. So our resultant force is our overall force. So that's our force forward minus our force going backwards. So if our force going backwards is increasing, therefore our overall forward force is going to go down, and our terminal velocity, so that's our maximum velocity, is going to be reached when our overall force is 0. And we also need to explain this DRS system. So that's a drag reduction system, so that's going to reduce our drag, and that means our resistive forces, the forces going backwards, are going to be reduced because we have less air resistance and less drag. Therefore, our resultant force is going to be not 0 for a longer time. The acceleration is going to occur over a longer time, so we'll get our terminal velocity reached in a longer time, and we might get a higher terminal velocity, so a higher maximum speed. It's going to have the same initial acceleration because that is when there wasn't any drag working on it. Like I said, we haven't actually done this topic in the kinematics module. We will come to it later, so don't worry if you didn't understand that at this point. Question 4. Figure 1 shows a golfer hitting a ball from the top of a cliff. It is at an angle of 34 degrees and they're hitting it at a velocity of 46 meters per second. Calculate the initial vertical component. So to go up, because our angle is to the horizontal, we're going to do 46 sine 34. So that's 46 times sine 34, and you'll get 25.7 meters per second, which, if we're going to give it to two significant figures, is 26 meters per second. And at point Y, the ball is level with its initial position. Show that the time taken to reach Y is about 5 seconds. So we're going to use our SUVAT equations. X equals 0, displacement equals 0. That is because we are talking about the vertical components here. And at Y and at the start point, they are the exact same height. There is no displacement from the height at which it started. Our initial velocity, we'll use our 25.7, so that we can be a little bit more precise. And our acceleration is minus 9.81. So I've got a minus in there. I don't always. It's because I've established our positive as up, because I've used 25.7. Sometimes if I don't have an initial velocity that's going up, I don't bother with the minus because I know that my answer will be correct. It will just be going down. But this time, because I've established this as positive going upwards, our acceleration has got to be minus because it's a deceleration. And t is our unknown. So the equation we're going to use, x equals ut plus half at squared. And we're going to write in all of our numbers. So this time our x is equal to 0. We are going to have a value here, 25.7 times t plus half times negative 9.81 times t squared. So there are two potential values that we're going to get for t here. One of them is just going to be 0 because the first time that the ball is going to be at height x is going to be when t equals 0, and I'll show you how we can work that out mathematically as well. So first thing we're going to do is we've got 0 equals, and we're going to factorise this equation. So you're going to have a t outside of the brackets, and then we've got 25.7 plus, actually it's a minus because it's 9.81, I meant to put there, divided by 2, and we'll just put a t because it was t squared. So there are two possible solutions to this equation. Either t equals 0, this t here, or this whole bracket equals 0. One of those brackets, well, if that was in a bracket, one of those has to equal 0 for this equation to be true. This is the first time that the ball is at x equals 0, so that's actually when it's hit off at the beginning, t equals 0. The thing that we want to work out though is we're going to say 0 equals 25.7, take away 9.81 over 2t, and we need to fully rearrange this. So what you're going to end up typing into your calculator is t is going to be equal to 25.7 times 2 divided by 9.81, and you are going to get t equals 5.24 seconds. If that was a little bit confusing for you, there is another way that we can do this equation. So I'm just going to move this all up so I've got a bit of space, and I'll do it in a different colour. We can also use the equation v equals u plus at. And what we're going to do then is when we hit off the ball, it goes up and then it goes down and it hits the place that we want. But halfway, it hits this point up here. And at that point there, we know the velocity is going to be 0 because it is changing direction. It's going from a positive to a negative velocity and it must go through 0 at that point. So if we can work out the time to get to that point up there and times it by 2, then we would have our overall time for this. So you might find this easier, you might find it harder, it's just another way. So if I write out our SUVAT again, we've got our initial velocity is the same, 25.7. Our acceleration is going to be the same, negative 9.81. We're still working out our time, but this time we know our final velocity at the top is going to be 0. So we can now put our numbers. So V0 is equal to U 25.7, 25.7 plus negative 9.81 times time. And if we rearrange that for time, we end up with C is equal to 2.61. So that's the time it took to get to the top here, and we also need then the time it takes to fall. So what we end up doing is timesing that answer by 2 to get our final time is equal to 5.24 seconds. So there's 2 different ways you could approach that question, both of which will get you the right answer, which is about 5 seconds. Question 4C. The total time of flight of the ball is 10 seconds. Show how the vertical component, so that's when it's going up and down, not across, changes throughout the whole 10 seconds. I'm just going to do a dot at 10 seconds to show that's where our graph's going to end. So we worked out earlier its initial velocity was 25.7. So we're going to do it 25.7, about there. A little cross because that's where we're going to start our graph. And then because we know that acceleration is going to be constant, it's going to be basically gravity, 9.81 meters per second. We could draw it from that gradient, but I find it easiest if we have a think about the curve that our ball is going to take. So I think this was labelled Y. So we've kicked off here. It's going to reach 0 at a time there, which we worked out in our last question, if you did the second method, was 2.61 seconds. So we can plot on the 0 axis, it's going to be around 2.61. If you didn't do that method, you can also have a think when it hits this Y point here, it's going to be at the exact same speed going down that it was going up at the beginning, 25.7 and 25.2. That's because we're ignoring any air resistance, we're just presuming this is perfectly accelerating due to gravity. So what we can do is at 5.24 seconds that we worked out earlier, so at 5.24 seconds, the velocity is also going to equal 25.7, but it's going to be in the other direction. So if I work out, that's 5, so 5.24 is going to be around there, and then we're going to do that at 25 as well, sort of there, and then you're just going to join them up with a nice straight line that's going to go all the way to 10 seconds. Hopefully they'll all cross through. It's not perfect, but I'm on the iPad, so hopefully you've done a better one in person. And you've got a nice straight line graph to show that acceleration is constant, going through all the points that we have previously worked out. Moving on to question 4D, calculate the height of the cliff. So there's 2 ways that we can do this, one of which is to use the area under the graph and calculate the area. So we do it between 5 and 10 seconds. Or roughly 5 and 10 seconds, because that's what we've worked out previously, is about when it starts going below this Y point. This is H to the ground. So we could work out the area there if you like, but I'm going to use SUVAT to do it instead. And I'm going to do it from its initial position. So we're going to say originally the displacement x is going to be equal to our height, h. Our initial velocity is 25.7. Our acceleration is going to equal to negative 9.81, and our time is going to be 10 seconds. So I'm going to include all of the time from the beginning all the way to the end, because that's what I'm taking our initial velocity as. And I'm going to use x equals ut plus half at squared. I'm going to pop in all of my numbers there. So I'm going to have 25.7 times 10, which is going to be 257, plus half times 9.81 times 10 squared. And I get a value of x equaling negative 233 meters. So it's a good sign that we've got a negative, because it's showing that our displacement x is going in the opposite way to our initial velocity, which we said was up. And that is quite correct. Our height is being measured down. If you did the area under the graph, or there are a few other methods you could have used, you'd have got something similar but slightly different. Question 4E, draw on figure 1 the path the ball takes when we account air resistance. So I'm just going to do a little sketch here. If this was our original one, if we have air resistance, it's going to come in to the left of it. It's going to fall quicker because we've got a force pushing it this way, making it decelerate horizontally. And we're on to our final question, question 5. The graph shows how vertical speed of a parachutist changes during the first 20 seconds of his jump. To avoid the air turbulence, he waits a short time before pulling the cord to release his parachute. Regions A, B and C show the speed before the parachute's opened. With reference to the forces, explain why the graph has this shape in the region marked. So similar to the previous 6-mark question, this one is about forces, and we haven't quite got to that module yet. We're just learning about the kinematics and the speeds and gravity. However, I've popped the answer here and I'll go through it with you. So in region A, the beginning bit here, first of all, we get a tiny bit of a straight line with uniform acceleration. So that's this bit of the graph here. So initially when he jumps out of the aircraft, he's accelerating just due to gravity. So the only force on him is his weight, which is his mass times the force of gravity. As he continues getting onto point B, his speed is increasing, but his acceleration is decreasing. So his change in speed, he's not accelerating as fast as he would. That's because there's drag forces on him. The air resistance starts to get larger the faster that he goes. And then region C, he's starting to reach his uniform speed, a terminal speed, his terminal velocity, the fastest he can go, and it remains constant for a little bit. That is because his resultant force, so the overall force is 0. So that means his weight going down is equal to the air resistance force going up. Okay, the next question, 5B, also uses the graph, so I'm not going to put the question up, I'll just read it. Calculate the maximum deceleration in the graph marked D. Show how the speed changes just after the parachute has opened. So because we need to show clearly, we need to show it on the graph. So we're going to be drawing a straight line, a tangent to the graph at the place that's got the steepest slope, the largest gradient. So I've had a little look, and the fastest bit that I can see is at this tangent here. So what we do is we read off our graph, what is the change in y, so divided by the change in x. What is the gradient? So here I'm going to do it with my entire straight line, so I'll do it across the graph, 50, take away 0, and I'll change in x if I have a look here. It's about 3.3-ish. So I type into my calculator 50 divided by 3.3. So I'm going to do 50 divided by 3.3, and I get 15.15 meters per second to the power of -2. So any acceleration around that would have been an acceptable answer. The mark scheme seems to say it's got to be 18 to 22, but I have done this correctly. So it could be a slightly larger deceleration depending on how you drew your tangent. Question 5C, use the graph to find the total vertical distance fallen by the parachutist in the first 10 seconds of the jump. Show your method clearly. So this is similar to the one that we did earlier. So we can draw the squares. So basically what we're doing is we're working out the area under the graph. I personally don't feel that's necessary. I've not seen that come up in the WJEC, but I'll explain what answer I got when I did it. So there is about 67 large squares. Each of them are worth a value of 5 meters. So you do 67 times 5, and it's about 335 meters under the graph in the first 10 seconds. Final question, during his descent he drifts sideways and hits with a vertical speed of 5 and a horizontal of 2. Calculate the resultant speed and the angle. So this one we can draw a formula triangle, not a formula triangle, a resultant force triangle. And we've got a vertical speed of 5, a horizontal speed of 2. We want to work out R, so we're going to do the square root of 2 squared plus 5 squared, which is going to give us 5.4 meters per second. So that's the speed. To work out the angle, let's work it out to the horizontal. This is our opposite, this is our adjacent. So we're going to do tan angle is equal to the opposite over the adjacent. So we're going to type into our calculators tan minus 1, 5 divided by 2, and you are going to get 68.2 degrees. And we've got to state that's to the horizontal, and actually the question did ask to the vertical, so I'll do 90, take away that to get it the other way. So I'm going to get 21.8 to vertical.